floor is yours.
All right. Thank you. Thank you, Mauricio, for the introduction. I'm going to share my screen. I think my screen is already being shared. Please let me know if you're able to see the title of the talk.
Yeah,
great. Thank you.
I thought it was, yeah, we were seeing it. Now I don't see it anymore. I don't know
you don't?
about others.
Let me check.
Gabriel, do you see?
I cannot see, no, I cannot see the screen yet. It's coming, apparently.
Okay, it's coming now. Yep.
But the slides are not there. Just
okay,
yes.
What about now?
It's fine now.
Great, thank you. All right, so Mauricio, thank you for that introduction. Just before we began, I was telling him, that before the pandemic-induced shutdowns in March 2020, SafeAI was the last workshop I physically attended in New York. And if this had been an in-person event, as was originally planned, I would have, come attended this as the first workshop since February 2020. But nevertheless, I am delighted to be invited here to give this keynote. And before I begin the talk, the obligatory disclaimer that I am not a regulator, nor do I represent a regulator, and all of the views expressed here and any errors are mine alone. So when I was asked to give this talk, I had to think quite deeply on what to say on certification of machine learning in aviation. And machine learning enabling autonomy is an extremely active field, over a decade old if we consider road vehicles. But it is only recently that some form of guidance is emerging on assurance and certification in aviation. So initially, I thought I'd give an update on my own work in dynamic assurance cases to sort of situate that within the context of the contemporary work. And so I looked up the existing literature to remind myself of the state of the art. And I found that there are quite a few articles in the literature with certification in the title or the body that go into the lower level details on how to specify, design, and verify various ML algorithms. And there have been many such excellent talks at this venue as well, such as the keynote yesterday and other talks earlier today. And there were also articles that I found on assurance and trustworthiness of autonomy implemented using ML, including basically my own work on dynamic assurance cases. There are some papers on applying specific existing aviation assurance guidance, such as DIA 178C. And there are plenty of papers on non-aviation related applications, standards, and certification in these domains, including addressing the requirements from standards such as the SOTIF standard, the ISO PAS 21448 on safety of the intended functionality, and UL 4600 on safety evaluation of autonomous products. And the more I looked, the more I realized that there are various silos of technically deep solutions in the current literature, and quite a few of them are related to aviation. Most are related to road vehicles. But there was very little that shed insight into certification as a practice. And quite possibly that's because a lot of that work is done in standardization bodies by practitioners who seldom publish. And there might be the perception that there is very little research fodder in the practice of certification. So I decided that this talk would be better given as a high-level examination of the nature of the certification and approval challenge for ML applications in aviation, so as to give an overview of the guidance and standards that are currently available, and to show the forest within which the various verification and assurance trees exist. And my intent is really to explore the additional practical challenges that there are beyond what has been identified in the current literature, and that I believe are ripe for research and for impactful solutions. And my hope is that this will motivate the researchers here to situate their work within the wider context. So this talk should rightly be named Navigating the Assurance Landscape towards Certification of Machine Learning in Aeronautical Applications. So quite a mouthful, sorry about that. But mainly we'll take a stroll through the landscape of assurance guidance, examine their relevance and role in certification, gauge their scope and applicability for assurance, and then I hope to conclude with some insights on where the research could benefit practice. I will not be talking about dynamic assurance cases, as I'd initially written in the abstract, but I hope that you will find the talk useful and interesting nonetheless. Right, so broadly there are airborne applications, air traffic management and air navigation service applications, and ground system applications within which ML and autonomy can be very beneficial. On the right, you see here a snippet from the IEEE spectrum article on urban air mobility and flying taxis. And these are the sort of the face of autonomy and the autonomy revolution in civil aviation. But there are, besides this, I'm sorry, what was that? Okay, sorry. But there are numerous other applications. For example, reduced crew operations and autonomous air cargo operations within the transport category aircraft. There is, of course, drone package delivery, air support services in firefighting and agriculture, law enforcement and infrastructure surveillance. And there are, of course, emerging aviation concepts. I already mentioned urban air mobility, but there is also advanced air mobility with electric and hybrid propulsion. And inevitably, certification and approval will be a key, if not the main barrier, to realizing this promise of autonomy. And for this talk, I'll mainly deal with the airborne category, although I believe the observations that I will make will apply to the ATM, AMS, and the ground systems domain as well. So certification, in my view, can be seen as another higher regulatory layer of safety mechanisms to assure the relevant stakeholders, in this case, the flying public and other third parties, that the air system is designed to be safe and will be operated safely through its lifetime. And indeed, there are many levels of certification, starting with the design approval or type certification, where a design for a particular type of aircraft or its engines will be accepted as safe and complying with the applicable regulations. And this is, in fact, design assurance. We have production certification, which provides assurance that manufacturing the aircraft fleet maintains the safety objectives of the type design. We have airworthiness and continuing airworthiness certification, which is an operational step to assure that an aircraft being deployed into service will be capable of safely initiating, maintaining, and terminating flight. We have equipment certification, which deals with specific kit that is expected to be installed and operated in an air system, such as an airborne collision avoidance system. But these are only the technical aspects of certification. There is also certification of many other elements of the complete air system, including the people, the air carriers, and the operators, and so on. And when considering software functions, such as what will inevitably be the implementation mechanism for machine learning, software itself is not certified. It is approved as part of the certification process. And sorry about that. And if there are tools that are used to generate the software, then eventually those tools will also need to be qualified. So as I mentioned when I started the talk, there were quite a few articles I found in the literature that allude to certification of various mechanisms for achieving autonomy. And this has included verification of machine learning, adaptive algorithms, agent-based models. And of course, there is a whole host of literature on modern assurance technologies, in particular safety cases or assurance cases, that speak of enabling certification. But really, many of these articles are actually referring to verification and assurance when they talk about certification. And all of these terms are related, but they're not the same. So I thought it would be relevant to introduce what I mean here when I refer to these various terms. You can read the sort of the definitions I put up there, and I realize this might be controversial, but I believe this aligns with the accepted definitions in the various guidance documents. And my goal is that by understanding the relations between each of these, we can assess the applicability of the various types of assurance guidance that is available for machine learning, where they fall short, and the additional work that is needed to close those gaps, which could be either fundamental or applied research. So let's take a closer look at this model. It's obviously minimal, and there are many more relations. For example, verification is not the only method of compliance, and there are other methods, including analyses, documentation, and so on. So a definition of a means of compliance is that it's a detailed standard, which could be, for example, a design standard, which, if met, accomplishes the safety intent of the regulations. And methods of compliance are a description of how compliance will be shown, which can include verification mechanisms, as I've kind of indicated here. This could be things like ground test, flight test, analyses. And as part of the certification process, the regulator determines what kind of assurance constitutes an acceptable means of compliance and what methods can be used to show compliance. And in the US, the regulator is primarily the Federal Aviation Administration, which issues what are known as advisory circulars that declare what they consider to be the acceptable means and methods of compliance. So I've listed here some of the regulation parts and corresponding advisory circulars. For example, 14 CFR Part 23 gives the airworthiness regulations for so-called normal category airplanes, which is the category under which many of the air taxi applicants will fall. And the advisory circular 23.1309 states the acceptable means and methods of compliance to the regulations of Part 23. So why is all of this relevant to machine learning certification? Because in fact, these documents state certain system level safety requirements that would need to be met, and that would have to be refined down from that system level to the requirements of the actual machine learning based functions or components. So for example, this advisory circular 23.1309 that I just mentioned, it gives some accuracy requirements for determining aircraft heading. And these would have to be directly translated into accuracy requirements on, for example, a machine learning based component that would be used to determine aircraft navigation parameters from, say, optical sensors. So my point here is that when there are research results reported on novel verification methods or testing for ML applications, what is often unclear is how those verification results actually relate to system level requirements. And therefore, it is difficult to say whether or not that verification technique will actually be useful within the context of the current certification regime. So in my opinion, one of the major gaps in the existing literature and the practice on ML verification and assurance is exactly showing the relevance of verifying low-level ML requirements on accuracy, robustness, coverage, and so on to system-level concerns. And some might say that that link is straightforward, but my response to that is that if that were true, we would have already had guidance or standards on detailing how this is to be achieved and shown. And as we'll see in the later slides, this is still an open question in both the existing guidance and the guidance that is under development. So moving on, there are at least 3 different categories of assurance guidance or standards in aviation. We have development assurance, performance-based standards, and goals or argument-based assurance guidance. Development assurance focuses on a standardized process to mitigate design and development errors. It is empirically based, which means it is typically formed by industry consensus that leverages their knowledge of successfully applied common practices. And so one way to think about development assurance guidance is that it specifies a process pattern in terms of explicit process objectives, process inputs and outputs, and process activities. Performance-based standards are focused on aeronautical equipment, defining concrete performance requirements, such as accuracy thresholds, response times, and so on. These standards are also consensus-based, and they are usually applied together with development assurance guidance. And an example of that is listed here, DO 386, which gives the minimum operational performance requirements on the new airborne collision avoidance system for unmanned aircraft, known as ACAS-XU. And finally, we have goals or argument-based assurance. And these generally give product-specific objectives, but limited or no guidance on the processes to be followed in meeting those objectives. And that is intentional. They are intending to be as broadly applicable as possible and giving the applicant the greatest flexibility in meeting the goals. However, there are few or any such, if any such guidance documents that would be applicable in civil aviation, at least in the US. And not least because many of these goals appear in the aviation regulations themselves, but at a system level rather than at the level of a particular capability, such as autonomy. So to summarize thus far, civil aviation certification, especially on the airborne side, airborne system side, has invoked development assurance guidance and performance-based standards. And I will mainly in this talk explore the available guidance on under development assurance and goals and argument-based assurance. All right. So what does this mean for certification and approval of machine learning? Well, for one, the existing guidance applicable to non-ML based systems and applications will continue to apply, largely because an airborne system is unlikely to be all machine learning based. And practically, the aviation industry has invested a lot of effort and money in defining these standards and the processes surrounding those standards. So they are unlikely to change significantly just because there is a new verification method or a new approach to testing ML. So from a research standpoint, a key question to consider for real impact is to show how the assurance and verification techniques will actually slot into these existing processes. And often I find that this is a question that is unanswered within many research papers. And one of the areas in my own work where we are currently spending some effort is defining how, for example, dynamic assurance cases will align with such development assurance processes. So some of the applicable guidance documents are listed here on the left. The most relevant ones, in my opinion, are ARP 4754, 61, and B178. And for machine learning in particular, the two that are relevant are the European Union Safety Agency, Aviation Safety Agency, or EASA's Level 1 guidance on ML applications. This was recently published in December, in fact. And the SAE's AS6983, which is currently under active development. And so in the subsequent slides, we'll look at this general approach to development assurance for each of these documents as it pertains to machine learning. So EASA's guidance gives a collection of safety and assurance objectives for ML and AI-based applications. It also gives candidate means of compliance, but these are not yet confirmed and they are still a proposal. This guidance is applicable to the full spectrum of aeronautical applications, including airborne, ATM, ANS, and ground systems. And it firstly classifies the applications into the 5 levels shown here. Level 1A and 1B are the most basic type of interaction, which is assistance to the human and supporting humans in information acquisition and analysis and decision-making support. Levels 2 and 3 respectively address the collaboration and increasing autonomy, but they are distinguished by the degree of oversight and capacity to override autonomous behavior. This guidance defines the notion of a so-called ML constituent, which is the yellow box that you see on the right. And basically, this is a collection of hardware or software items, including the necessary pre- and post-processing elements, and at least one specialized hardware or software item which contains one or several ML models. So starting from this notion, it gives some objectives and guidance on trustworthiness analysis, which includes safety analysis, the learning assurance process, on explainability, on safety risk mitigation, and also on how to tailor the guidance such that the assurance that would be obtained is proportional to the risk posed. The guidance document is quite long and it's freely available, but I will try and describe what I think are the salient features. So first, there was in the document an emphasis on proper description of the operating context, and not unexpectedly sort of the data needed for defining the ML application scope. So it adopts the term ODD from the connected and automated vehicles, or the ground vehicles domain. And there are adjustments to the safety process. In particular, there is a requirement to establish and evaluate failure modes of an ML item. And so this is most likely to be fulfilled with a failure modes and effects analysis. But there's additionally an objective to determine what they're calling ML constituent reliability. And in my opinion, this is sort of a major departure from prevailing safety analysis guidance, which has traditionally issued software reliability. And in addition to that, it introduces a W-shaped learning assurance process, which is conducted alongside the systems and the non-ML software and hardware V processes. So as you can see here, each process has a number of steps, and each step has a number of objectives. And I've listed here in parentheses the number of objectives there are for each of the process steps. And on the right here, the inference model verification, data verification, and constituent verification together share 5 objectives. And the data management phase has about 11, which is the most out of all of these. And in addition to these objectives, simply for learning assurance, there are about 17 objectives on explainability, 2 on safety risk management, and 14 objectives on trustworthiness analysis. So the main takeaway in terms of applicability of the EASA guidance is that the proposed objectives and means of compliance will not affect the existing regulations and the means of compliance for the non-ML parts of an airborne system. And the current regulations will not change at the system level, but there are additional objectives that will need to be fulfilled for ML applications. And this guidance here gives a proposed means of compliance. The guidance mainly applies in the European Union, so at the moment it is not possible to comment on how this would affect certification in the US. And to address this, there is an ongoing effort in the SAE to create the standard AS6983 for certification and approval of aeronautical products that will integrate machine learning and other AI capabilities, which is what I will talk about next. So this effort is still in its drafting stages. So unfortunately, although a lot of progress has been made, I cannot give very specific details. All I can say is that the EASA regulators are part of this effort. And therefore, when the standard is finalized, it will be aligned with the EASA guidance that we just saw. However, there are some major differences in this effort relative to the scope of the EASA guidance. Firstly, it is likely, in my opinion, that the system safety process itself will or could include additional analyses beyond what is recommended in ARP 4761. And although the EASA guidance mentioned modified the system safety process, the main modification was an FMEA. However, in this standard, we are exploring the introduction of maybe FMEA and maybe additional safety processes at the item level. And there's a proposal to assess the hazards posed by the definition of the ODD itself. So as such, there is a proposal for a data hazard analysis starting at the system level and then moving down through the refinement of the V. Secondly, the EASA guidance described assurance levels mainly on the ML component. And this will also be the case for AS6983. However, there is also an assessment and alignment of development assurance levels at the higher functional and system levels. The EASA guidance does not give process guidance on developing an ODD, but within AS6983, we're currently investigating this quite actively. Fourth, where the learning assurance process in the EASA document had a W shape, here there are two specific processes that are being introduced. One is called the Machine Learning Development Lifecycle, or MLDL, and the Machine Learning Item Development Lifecycle, or MLIDL. And the associated process guidance for both the MLDL and MLIDL at the moment is far more detailed, with artifact development objectives and properties being documented. And so the ongoing effort is in tailoring those process objectives in a manner similar to what is found in DO-178C. So the assurance of machine learning would be seen as aligned with the principle of DO-178C, which is to, and I'm paraphrasing, apply the development rigor such that ML items and constituents perform their intended function at an acceptable level of safety. All right, I will now move on to goals and argument-based assurance. So although I've titled this category of assurance guidance as goals and argument-based assurance, the actual guidance documents mainly give assurance objectives and guidance by way of examples on achieving those objectives. And then depending on the document, there is either an implicit or explicit allusion to structured argumentation. And so I have grouped these documents under this common category. The first document that I'm considering is the SCSC-153B, which is the version 3 of the guidance produced by the Safety of Autonomous Systems Working Group, or SASWG, of the UK Safety Critical Systems Club. In fact, there are a couple of the authors of this document who are in the audience today. So I hope I do them justice when I summarize the content of this. And this document gives a domain-agnostic collection of objectives that is intended to provide assurance that an autonomous system in general, or a system implementing machine learning in particular, will be safe. Then the Assuring Autonomy International Program out of the University of York, also in the UK, has two sets of guidance. The first is a pan-domain body of knowledge, which is still being developed. This document also gives a collection of assurance objectives, along with some system safety argument patterns. And the second document is a more safety argument-focused guidance titled The Assurance of Machine Learning in Autonomous Systems, or AMLAS. And this document gives a process and a collection of argument patterns that cover the different stages of the machine learning lifecycle. And the last document as such are the overarching properties work. And this refers to an effort that is being spearheaded by the FAA to establish a minimum set of properties that are sufficient for certification. So I will go through each of these documents in the next few slides. SCSC-153B is intended to be broad in scope and addresses autonomy as a capability. And so its guidance could be applicable for both supervised and unsupervised learning, as well as reinforcement learning. And by design, it does not tie itself to a particular development approach, lifecycle, or safety argument. And it gives a conceptual framework that is shown here with a platform level, an autonomy architecture level, and a computation level. The computation level is the lowest level, addressing the input-output mappings, which would be implemented on a hardware or software infrastructure. The platform level is the highest, representing the functions, services, and other capabilities that are to be provided. And therefore, it addresses the autonomy requirements. And the autonomy architecture is the middle layer, which embeds the computation into the platform. And associated with each of these layers are so-called projections, which are essentially different viewpoints on each layer. And the purpose of these projections is to elicit the various objectives. So for example, I've listed 3 of the projections here associated with the architecture level. And these are tolerance of faults and failures, provision of information at the relevant interfaces, and facilitating adaptation. So there are 11 objectives for the autonomy architecture, 15 objectives for the platform, and 19 objectives for the computation. I would say that the document, as I mentioned, is not tied to a particular development approach. And I think that this is both its strength and its weakness. It's a strength because it has very broad applicability and it covers the autonomy stack from platform to computation. But by seeking to be broad, it has limited itself in its applicability in the context of certification. And in particular, as I will show in a couple of slides, application of the objectives to specific types of ML architectures may not be as straightforward as one would like. So before I show that, here are some of the objectives for the computation layer emerging from the algorithm projection. I've listed what those objectives are. So you have to show that an appropriate algorithm type has been used, that the typical errors are identified and protected against, the behavior is explainable, and that there's support for post-incident analysis. And one takeaway that I sort of gleaned is that in this model, the ML algorithm is viewed as an atomic concept. However, I think that it is unclear whether it suffices to view an algorithm as atomic. On the right here is an example that I've abstracted from an actual aviation application, which is to be implemented using machine learning, where it is unclear how this functional hierarchy on the right matches up with the layered stack from the guidance. So for example, one question is whether the neural architecture is better mapped to the autonomy architecture layer or to the algorithm projection of the computation layer. And if we were to consider the neural architecture as a structural representation of an algorithm, then a subsequent question is whether additional objectives are required with respect to the logical model architecture, which embodies the algorithm projection of the computation, versus the deployment architecture, which allocates the neural network or the neural architecture to a combination of hardware and software. In other words, are the objectives that have been identified at the algorithm level sufficient? And do we need additional or more objectives for the deployment architecture? So to summarize, the guidance of SCSC-153B is quite comprehensive in breadth of applicability, but will require additional work to be applied to civil aviation. There's basic guidance on tailoring the objectives for proportionality of assurance, which is commensurate with the safety risk post. So it refines the high-level objectives it has identified to objectives on process outcomes, but the rationale for those lower-level objectives is implicit, and I believe this could have been justified as a structured argument. But it is a good starting point and could be useful for elaborating particular process objectives and related process guidance. And in fact, this is the path that some of us are taking in crafting the AS6983 process standard for development assurance, which we looked at earlier. Next, we'll look at the Assuring Autonomy International Program's body of knowledge. And this provides assurance guidance organized around a conceptual framework that comprises 4 themes, which are as shown here. And this guidance also seeks to be as general as possible, but aims to provide domain-specific guidance. However, up until date, most of the applicable guidance that has accompanied the objectives consist of example applications in domains other than aviation. But this document is an evolving document, and so the guidance can be expected to be refined and clarified over time. And for each of the areas, the guidance is organized around assurance objectives. So for example, in the defining required behavior theme, this involves objectives around hazard identification, determining hazardous system behavior, defining safety requirements, and evaluating the security on safety impact. And each of these objectives themselves have sub-objectives, which are not listed here. But for example, one instance would be for hazard identification, there is guidance on defining the system scope, the operating environment, and the operating scenarios. And for application to aviation, at least the objectives of defining the required behavior and controlling deviations from the required behavior can be mapped into some of the existing process guidance at the system level, for example, in ARP 4754A. But where this body of knowledge is unique is in defining assurance objectives for the implementation of the required behavior. Specifically, it subscribes to an agent model of autonomy, which constitutes the so-called observe, orient, decide, and act, or OODA loop, or equivalently in this case, the sense, understand, decide, and act loop. And broadly, the guidance for each of these functions is organized around defining the requirements for each function, defining the infrastructure requirements for implementation of each function, and then validating the requirements. There is additionally guidance on the implementation of requirements using machine learning, plus additional system level objectives such as interactions within the system and within other systems and so on. So how does this apply within the context of certification? Well, the body of knowledge states that it is aiming to be as general as possible, only as specific as necessary, but providing domain-specific guidance where required. But unfortunately, as noted here, the aviation-specific guidance is yet to be crafted. And so at present, it needs to be adapted from guidance available for other domains, and this may not be straightforward. For example, the guidance on identifying potential deviations from required behavior suggests the use of safety contracts and developing argument-based safety cases. And while this may be applicable in the general scheme of things, it is unlikely that that would find immediate application in the current civil aviation practice, at least not where airborne systems are certificated. Similarly, the adoption of the sense, understand, decide, and act functional agent model is, in my opinion, orthogonal to the representation of the system as compared with the traditional aircraft functional organization, which is one of the main starting points of a functional hazard analysis. So it is yet to be analyzed what this means in terms of deviating from the established system safety processes. And where the document goes beyond the SCSC-153B guidance is in providing a system level safety argument. However, when addressing component level safety requirements, it stops at model verification, which is a layer higher than verifying the implementation of the machine learned model on the flying platform. And so the safety argument and associated evidence would need to be further developed before it can be considered for use. Nevertheless, like the previous document, it too is a very good starting point to organize development assurance guidance that the regulator is likely to endorse as a means of compliance. Moving on, assurance of machine learning for use in autonomous systems, or AMLAS, gives both an assurance process and a collection of argument patterns covering the different stages of the machine learning lifecycle. And the methodology as shown here comprises 6 stages, which are conducted sequentially and iteratively. And at each stage, there is an underlying process that occurs alongside the process for ML component development. For instance, the process of model learning assurance has steps related to creating the ML model, testing the ML model, and then instantiating an ML argument pattern, which I've shown here as a tree of claims and evidence. And the evidence would in fact be instantiated from a particular process applied to a particular ML component. And then the steps 3, 4, and 5 that are highlighted here directly relate to the 3 objectives of the body of knowledge that we saw just before the slide under the assurance of the ML implementation of the SUDA function. So how does this apply for certification? Well, it assumes a particular learning process, and we will need to see how it actually aligns with learning assurance processes that are defined by consensus in the aviation industry. So it is not straightforward to see how the AMLAS learning process aligns with the W-shaped process or the MLDL and the MLIDL in the SAE AS6983. And any changes in the process will almost surely alter the process objectives and the corresponding assurance goals. And as yet, there is no guidance in this methodology on how to tailor the AMLAS process. Similarly, tailoring of the assurance objectives so that assurance is proportional to the risk posed is missing. And this is a central facet of the safety engineering for aeronautical applications, since not all applications or functions have the same criticality. So the underlying arguments that are proposed in this framework require a means to select the objectives and evidence required that apply relative to the safety criticality of the applications. It emphasizes safety argument creation based on pattern instantiation. And although, as with the previous document, this may be a good practice in and of itself, there is no clear path at the moment for its use in certification of ML applications in airborne systems, at least in civil aviation. However, this approach would be synergistic with the regulations applicable for approval of ANS and ATM systems, in particular in Europe. The assurance objectives identified in this methodology well cover the objectives of the previous two documents. And lastly, a common thread for all of these documents we have seen so far is that it is a good starting point for elaborating process-specific guidance. I'll quickly talk about overarching properties. These are basically referring to an effort that is spearheaded by the FAA, including NASA and other regulators, and some industry stakeholders, which are collectively known as the Overarching Properties Working Group. And the properties are listed here: intent, correctness, and innocuity. I won't go through the definitions, you can read it. But basically the idea is they are supposed to constitute a so-called sufficient set of overarching properties, such that if it can be shown that these properties are possessed by an aeronautical product, then that product is fit to be approved. The documentation that is available is quite ambitious in that it seeks to be an alternative means of compliance instead of development assurance, but it would augment rather than replace the existing means of compliance. There's a typo there. And the underlying goal is to rely on argumentation to show that the aeronautical product possesses these three properties. So with respect to applicability to machine learning, assurance essentially would require demonstrating that an ML-based application meets these three properties. So to summarize, I've given here a comparative assessment of the various guidance documents we have looked so far along various dimensions. And this is an assessment that I put together primarily for this talk, but I'm currently working on a paper that will give a more principled assessment. But I think this gives a good overview, I think, of some of the assurance considerations and principles that are being considered by the documents. For instance, by their very nature, development assurance guidance gives very high-level product objectives, more detailed process objectives, repeatable and predictable guidance due to industry consensus, and the regulator knows what to expect. Whereas goals and argument-based guidance gives more comprehensive product objectives. There is limited process guidance since the intent is meant to be as flexible as possible. However, because of this flexibility, the regulator may not know what to expect if an argument-based approach is employed. And therefore, in their current form, there may not be much room for their application to certification in civil aviation as of yet. To conclude, I am going to propose some areas where I think research could close the gap between the state of the art and the state of the practice. The first, I think, is safety analysis adjustments at the system level. And in particular, new safety analysis techniques for ML items, in particular neural architectures, and the data that is used to train the models. John McDermid at the University of York has some very interesting ideas on this. Then linking verifiable ML properties to system safety impact, and additionally, this relates to linking machine learning metrics to system safety. I find that there is little work on that. Then architecture-centric analysis and machine learning reliability metrics. This could be a potential way forward to address some of the objectives that have been set forth in the KIASA guidance. And lastly, a more rigorous basis for the proportionality of assurance and the selection of objectives, especially when using structured arguments. And the underlying theme in these topics is mainly to situate the research within the context of the existing certification framework, especially as it applies to certification of aeronautical systems, including machine learning. And I know that some of these areas that I've proposed may not seem, as sexy as a brand new formal verification technique for some machine learning property or a new algorithm for some novel network architecture. However, unless those techniques and properties can be shown to be relevant at the system level, their practical impact from a certification standpoint will unfortunately be minimal. Thank you. That is my talk, and I am happy to take questions now.
Thanks, Ganesh. I think we have time for a few questions, maybe from the audience. Do you have any questions? Otherwise, I will ask my questions. I'll give you a few seconds. I don't know. Wanted to give you guys the opportunity to ask. Okay, since I am chairing this session, I will ask a couple of questions. Ganesh, you mentioned a few interesting, research topics. One thing that I think that may be missing is this the effort to assess, whether it's compliance with the process, or how solid, let's say, in your assurance cases. I think one thing that is missing is sort of helping assessors, right, evaluate, get a sense of being able to understand the evidence that was provided against the risks that they know about, when they formulated the let's say the high level requirements for the system. And I see that as a major gap, and especially for machine learning, where a lot of the knowledge resides on the developer side, and for someone who is coming as an external evaluator, right, it's easy for them to quickly grasp what was done, what was not done, what are the deficiencies.
That's an excellent point. I think that this is one of the challenges, certainly with argument-based assurance and goals-based assurance, because the regulator ends up getting, different arguments for the same objectives, and it's, I think, still an open research challenge as to how a regulator should consistently evaluate the different arguments that they're being given. And I think, as a consequence, what is likely to be the case in certification is that development assurance is not going away, because it gives the regulator some very predictable ways to assess whether a product complies with the regulations. They put forth these advisory circulars because they have been involved in the process of standardization, and they know what to expect. However, what I found in development assurance guidance is that the process guidance is very detailed, but the link to the product objectives are somewhat weak. So the approach that we are taking in AS6983 is to take the argument-based or the product-based guidance that has set forth these objectives, and use these to determine, what our processes have to be. So one ends up with sort of a combination of goals-based assurance with argumentation providing rationale within standardization to develop process guidance. And I think that this is useful because it provides assurance at the standards level that the standard you're developing is sufficient for use. And it provides some flexibility to determine what processes are needed. And at the same time, it gives the regulator some confidence that what they are receiving is predictable, and that would reduce the certification effort on their end. But I would say that this is speculative, and this is my viewpoint. Whether or not this would actually be followed, I don't know. I would say that within AS6983, that's the approach some of us are taking in order to craft the process guidance. So we start with the actual product-specific objectives. So we're looking at the SCSC-153B, the AMLAS, and the BOK guidance, and thinking, well, given that we have these objectives, how do we refine these into lower-level objectives? And what is the process that is needed to actually get these lower-level objectives? And can we then get consensus that this process actually makes sense, and then provide guidance on that process? So that's the approach that some of us are taking. I don't know if that answers your question, Mauricio.
Oh, thanks. Yeah, thanks, Ganesh. We could, if we were in person, we can talk much longer.
Right.
yeah, about these topics. Maybe we have just a little bit of time for maybe one more question, and then we have to switch to the next session,
Sure.
I think.
Yes, I hope I didn't put the audience to sleep.
And
All right, we have no more questions. Maybe I
okay.
can call upon Jane Fenn or Philippa Ryan. Do they have any questions?
Hi, okay. Okay, I'll stop. I've been trying to formulate my question, which is, you talked a lot about the regulator, but I feel there's perhaps a gap in, I'm trying to work out how to say this sort of well. You know, you need to the regulator needs the technical understanding to understand the assurance they're being given on machine learning. And given that many of us don't have that understanding yet as what is good assurance for machine learning, I feel
Right.
like we're a long way off from.
I completely agree. And
Yeah.
in fact, I think that the approach EASA has taken, which is to really limit the scope of their guidance to really low criticality applications. In fact, the guidance is for level 1 or 1A and 1B applications. And they're looking primarily only at supervised learning. And they're saying that the guidance that we're giving is for applications with extremely low criticality, level D. And these would be applications where the pilot is in the loop and all the machine learning system is doing is giving them some guidance, and the pilot can say, well, I don't accept it, right? We are nowhere near the point where we can deploy, you know, machine learning based navigation for Autoland. In fact, that is a very cool application that some of the groups are working on. And the precursor to the EASA guidance was, in fact, exactly this, Autoland systems, but Autoland in the context of providing guidance to the pilot rather than taking over the control. In defense aviation, I would say that the sort of risk tolerance is much higher, and so perhaps there are more sort of there's more flexibility, I guess, to implement or deploy some higher risk ML applications. In fact, I think towards the end of last year, there were two firsts. One was this update of software in a flying platform. Mauricio knows what I'm talking about. And I think the second was the use of an AI system on a B-2 bomber to provide radar targeting. But again, I would say that the second application, which was using AI for radar and providing pilot assistance, was not a safety critical application, right? So, and moreover, the platform was extremely constrained. The people who built this knew the system in and out, right? And it's one of a kind. But if you want to deploy this on a fleet and you have variants, then it's a completely different story entirely. So I would agree with what Philippa is saying, that we are a long way away. And one only needs to look at the road vehicles domain, who have been promising us self-driving cars since 2011. We were supposed to have self-driving cars. We do have them, but whether they're safe is a different question.
Yeah.
I was just going to interject there, Ganesh. So the military side, it depends on which side of the pond you are in terms of the risk appetite for military, because certainly in the UK, the military are the regulator part of the MAA part are very extremely conservative and insist on standards that say that the human must make the ultimate decision. There is no way that we allow AI into our decision-making process, and we won't allow it to learn in usage. So it's got to be very tightly configured. So they are very at the moment that they are very unwilling to have discussions about risk sharing, but they are backing a lot of research in the area. So it's kind of mixed messages at the moment.
Yeah, indeed. I would say that in the UK, it's a sort of a unique situation for argument-based assurance because it sort of originated there. So the regulator there, at least the MAA, and certainly the MOD, buy into this. But in civil certification here in the US, I think it's still an uphill battle. So I would say that development assurance is not going away. There is obviously ample evidence that it works, but where I think argument-based assurance could be helpful is in fact in the crafting of the standards themselves. I think that this is a slightly different way of looking at things, but there you have it.
It's a good ambition. I like it. I need to talk to the people who are doing the research for the MOD over here about different cultural ways of working in the future. So that's definitely part of the discussion.
So for the rest of the audience, Jane is actually part of SAE AS6983 crafting. So yes, I'm looking forward to working with you, Jane.
Thanks, Ganesh.
I should also say that people were interested in tools for GSN and assurance cases if you wanted to take that opportunity, Ganesh.
Oh, certainly, yes. So we have our advocate tool for GSN and assurance cases. So look us up on the web, and the tool is called Advocate. So shameless plug for that.
Thank you.
Okay.
Thanks, everyone. Thanks, Ganesh.
Thanks, Mauricio.
Thank you. Now I think we'll move directly to our session 5, where I think we wanted